Bienvenue tout le monde au colloque des sciences mathématiques du Québec. Welcome everyone to the CSMQ. So our speaker today is our very own Dmitry Faifman here at the Université de Montréal. So to tell you a little bit about him, because he's pretty new here, joined us this year. Wonderful. So Mitya did his PhD at Tel Aviv University with Semyon Alaska and Vitaly Milman, and then did 3 postdocs, and one in Paris at the Institut des Hautes Études Supérieures, one at U of T, and one here at CRM, where I believe you were actually based at UDM. Is that correct?
I had 3 bases,
okay.
actually, in McGill, in Concordia, and here.
Okay, well, that is part of the fun of our city. You get to go all over the place. And then was a senior lecturer at Tel Aviv University until we stole him last year and brought him over here. And so we're very happy to have him telling us about different parts of geometry. And so his talk today is called Almost All Roads Lead to Func Geometry. So please give a welcome to Mita.
Okay, thank you very much for the introduction and for invitation to speak here. I'm very happy and very honored to be here. So I will talk about work that actually started during my postdoc here in conversations with Alina. And then it became clear that what we're talking about is func geometry. And later on, I worked on it also with Constantin, Vernicos, and Cormac Walsh. They will appear later. So let's start in a bit of history. It goes back to Hilbert. Hilbert's first problem, or the problem of the straight line as the shortest distance between 2 points, in modern language can be phrased as follows. So you're given a convex domain omega in Rn, or in projective space, and Hilbert asks to find all metrics in this domain for which straight segments are geodesic. Such metrics are nowadays called projective. And for symmetric metrics, this problem was largely solved by Buzman, who gave a construction, and Pogorelov, who showed Buzman's construction was general. In the non-symmetric case, for non-symmetric metrics, the problem remains open, actually. So here are the examples that Hilbert had in mind when he was asking this. Of course, the Euclidean geometry or the spherical elliptic geometry in projective space. Then there is the hyperbolic geometry, particularly the Beltrami-Klein model of hyperbolic geometry in the ball. There is Minkowski geometry, which I will talk about in a moment, and an example due to Hilbert himself, which is most closely related to us, the Hilbert metric in the interior of a convex body. So one word about Minkowski geometry. It will play the same role for us as Euclidean geometry plays in Riemannian geometry. It's the infinitesimal model. So Minkowski geometry really is just normed geometry, except the norm need not be symmetric. So how does it work? You start with some convex body K in Rn such that 0 is in the interior, and it defines a norm in this simple fashion. You look how much you need to rescale a vector until it hits the boundary, and this gives you a distance for which K is the unit goal. And now Hilbert geometry. First, let's recall the Beltrami-Klein metric. So you start with the Euclidean ball, and you have 2 points x and y. You want to measure the distance between them. What you do, you extend until you hit the boundary in points w and z. You form the cross ratio. So xz divided by yz times wy divided by wx. Take the logarithm. There is some normalizing factor, which doesn't play a big role. And that's the distance. The Hilbert metric is exactly the same thing, except you start with an arbitrary convex body, but then you use the exact same formula, the logarithm of the cross ratio, 1/2. Gives you a metric on the interior, and Hilbert showed that this is in fact a projective metric. Straight segments are geodesic. So the cross ratio is a basic invariant of projective geometry, and that means that the Hilbert metric is a basic geometry, is invariant under the transformations of projective geometry and their collineations. And it's very useful when you study projective structure on manifolds. And yeah. Another example, which was constructed later, came from Hilbert's student, Paul Funk. So in 29, it's very hard to find his photos on the internet. That's all I could do. Gave the following construction. So again, we start with a convex body with non-empty interior. And we're going to construct a Finsler metric in the interior. So a Finsler metric is the same as a Riemannian metric, except instead of having an inner product on each tangent space, you have a norm. Now, a norm, more precisely, a Minkowski geometry. So it's the same as a unit ball, some convex body. So to specify a Finsler structure, we need to specify a convex body in every tangent space. And here comes the tautological Finsler structure on the interior uses the same convex body for all the tangent spaces. So at this point, we have this unit ball. At this point, we also have the same unit ball. What changes is the position of the origin. So what you see here are two unit vectors. This is a unit tangent vector at this point, and this one is a unit tangent vector here. So it's not Minkowski geometry. It should remind you of hyperbolic geometry, right? This is more or less what happens when you start coming close to the boundary. The arrows that look small to our Euclidean eyes still have length 1. And it reminds you of hyperbolic geometry for a good reason. We will see in a moment the exact relation. So, of course, it is an affine invariant construction. One can compute the resulting distance. Turns out that you do the following simple thing. You extend, as we did for the Hilbert metric, for the interval from x to y until it hits the boundary at z. And you just compute the ratio xz over yz, take the logarithm, and this is the resulting Funk distance. Of course, it is non-symmetric. It never is. And once again, one can show that it is a projective metric. Straight segments are geodesic. Moreover, as you see from this formula, if you symmetrize this distance in the most straightforward fashion, you get the Hilbert metric. So in a sense, the Funk metric is more fundamental than Hilbert, easier to study, and in a way has nicer properties. Let's look at a couple of examples. We already mentioned that the Hilbert metric in Euclidean ball is just hyperbolic geometry. But now let's look at the Funk metric at the same Euclidean ball. Turns out it's almost the same thing. So the Beltrami-Klein hyperbolic metric and the Funk metric differ by some potential function. So there is some fixed function written here such that the distance between 2 points for the two metrics differs by this potential. And this has strong implications. For instance, if you have some closed curve, then it doesn't matter which metric to use, you'll be getting the same answer. Also, if you want to play billiards using the metric, doesn't matter which metric to use. The potential doesn't change the billiard reflection law. Another example, if you look at a simplex, for example, then the Hilbert metric in its interior is going to be a known space. This actually characterizes the simplex uniquely. And similarly, if you look at the Funk metric in an octant, then you'll be getting some kind of degenerate normed geometry. Okay, so just like in Euclidean geometry, we can look at billiards to learn a lot about the geometry, and this is even more true in Funk geometry. So let me try to convince you. First of all, a reminder, what are billiards? We have some domain, omega, which will be our billiard table in the interior of K, where we have the Funk metric. So the billiard, we say that 3 points Q0, Q1, Q on the boundary of omega are consecutive points of a billiard orbit if, when you look at this length function, which is the distance from Q0 to x plus the distance from x to Q2, it's important to care about the order of the points because the distance is non-symmetric, then Q1 should be a critical point of this length function. This gives us the reflection law. Now, Gutkin and Tabachnikov some years ago discussed Finsler billiards in general and characterized the reflection law. So in the case of Funk geometry, it's the following very aesthetically pleasing construction. So we have a ball that goes from Q0 to Q1. So we extend this line until it hits the boundary of K, which defines the geometry. So it was going in the direction of P0. Now we draw two tangent lines or hyperplanes. Let's pretend it's two-dimensional. So lines, they intersect somewhere. Now we drop the other tangent to RK. It is tangent at P1. This is the new direction in which we will be going. And going back to my remark from earlier, if you start with K, which is the Euclidean ball, then this is the exact description of hyperbolic billiards. So a very geometric description. And one thing catches the eye when you look at that. This construction is projectively invariant. Even though the Funk metric is only finely invariant, somehow here we only talk about lines, intersections, and tangents. And this is for a good reason. So it turns out that the Funk geometry is, contrary to what you would expect maybe, almost projectively invariant in the following sense. If you have some collineation G, which keeps K away from infinity, so G of K is still a convex set, then you have the Funk geometry in K, you have the Funk geometry in GK. You have 2 points. You can measure compare the two corresponding distances. And again, they differ by a potential function that's independent even of the body itself, some universal function. There is maybe even a slightly better, maybe more useful way to think about it. So think about K as a body inside projective space. Then to turn it into a affine space, you need to choose some hyperplane at infinity. So for each such choice, you get a convex body in affine space and the Funk metric inside. And so those two metrics, they differ by a potential function of this very simple form, just essentially the logarithm of the ratio of the two affine hyperplanes. This again has immediate consequences. For instance, if you have a submanifold of inside K and you induce the Finsler structure in it, so a curve is a geodesic on this submanifold. If it is a geodesic, then it's also a geodesic for the image of this whole thing under a collineation, and the length of closed geodesics would be preserved. And similarly, as we have seen, the billiard reflection law is the same, and the length of closed orbits would be preserved under collineations. It is PGL n plus 1, just an invertible transformation of projective space. Good. So now we're going to talk about volume. It turns out that volume in Funk geometry is closely related to the volume product in a classical invariant and convex geometry. So let's first recall that. So we will be making use of the polar body. What is the polar body? If K is the unit ball of some normed space, then K polar is the unit ball of the dual space. It consists of all the functionals which are less than or equal 1 on all of K. And we will be taking polars with respect to different points of inside the body. So we will be denoting by kx the polar of A with respect to x plane 0 of the origin. Good. The volume product at x is just defined as the volume of k times k polar at the point x. Now notice that this body lives in Rn times Rn star, the dual Rn, so there is a natural volume form in that space, and that's the volume we take. Okay, so it turns out that this function is a convex proper function of the point x, which we're looking. So we define the volume product as the minimum of all such things. And it's useful to know that, in fact, the minimizing x is unique. It's called the Santaló point. And it's useful, for example, if your body has central symmetry, then 0 must be that very point, right? Because the point is unique. Good. So what does it give us? It gives us some functional on convex bodies, which is invariant under any affine map. Translations, of course, so GL. And that means that we have a continuous function on the Banach-Mazur compactum, which is just the quotient of the space of convex bodies with non-empty interior by affine maps. And that means there are extremizers, and it's natural to look for them. And people did. And for the maximum, this problem is completely solved. Blaschke-Santaló inequality asserts that the maximum of the volume product is attained by ellipsoids. The minimum is a much more complicated story. So Mahler in 1938, he looked at this quantity in relation to geometry of numbers. And he showed that the simplex minimizes for n equal to 2. And he conjectured that's the case for general n. To date, n equals to 2 is the only dimension where it is known. And there's also a centrally symmetric version of this question. So to state it properly, we will need the notion of a Hanner polytope. What is a Hanner polytope? Here is a recursive definition. A Hanner polytope is either an interval or the Cartesian product of Hanner polytopes or the polar of Hanner polytopes. So your building blocks are intervals, and you're allowed to take products and polars. Anything you arrive at is a Hanner polytope. The cube is an example. The cross polytope, it's polar. There are many others. And here is Mahler's symmetric conjecture. So for centrally symmetric convex bodies, this is the conjectured lower bound for to the n over n factorial. And it is expected to be uniquely minimized by Hanner polytopes, of course. Well, that's a conjecture, so you can conjecture whatever you like. There are no other known equality cases. Okay, this is known for in the two-dimensional, and also the three-dimensional case has been recently fully resolved. Higher dimensions remain open. There are nevertheless some partial results in higher dimensions. Here are some of them. So if you assume some symmetry for the bodies, for instance, if you have the symmetry groups of the cube or of the simplex, then it is known that the minimizer is the cube or correspondingly the simplex. Also for bodies of revolution. So if your bodies are symmetric enough, it seems easier. For zonotopes, which are Minkowski sums of intervals and their limits, Mahler is known. Also for polytopes with a few vertices, due to works of Lopez-Reisner, Karashev, and Meyer-Reisner. And finally, actually using some symplectic geometric tools, Karashev, using results of Belitsky, also showed that LP balls, that hyperplane sections of LP balls and and Hanner polytopes are also, well, satisfy the Mahler inequality, the Mahler conjectured inequality. So there's some strong evidence, but no proof. Another kind of sport that people were involved in is trying to prove an approximate Mahler inequality, so with some constant to the end. So that already was a breakthrough that a constant exists. That was the theorem of Bourgain and Millman from 87. And the currently best constant is due to Greg Kuperberg. In a very beautiful paper, he obtained the value of pi/4. I think beating Nazarov's constant by a factor of 2 or something like that. Okay, so let me briefly mention the billiard connection. So there is a good reason to discuss both volume and billiards at the same time for the following reason. So the Viterbo conjecture is, or rather was, the following statement that for a convex body in R2n and C a symplectic capacity, let me not define it. I will give an example that will be the main example for us. But some symplectic measurement C, there is an inequality between the symplectic capacity and the volume of omega. Equality attained by the Euclidean ball, but not uniquely, by its symplectic images, of course. Okay, so a special case of this conjecture uses a capacity that comes from Minkowski billiards. So here is the bottom line. For K and L, let us denote by psi L of K, the shortest periodic billiard orbit inside K, where the billiard is with respect to the norm of the metric defined by L. This gives a capacity on this body inside R2n. And so this was observed by Arstin, Avidan, and Ostrover. So the conjectured inequality would be that the least billiard orbit inside K with respect to L is bounded by the volume of K times L polar. And then you take K equals to L, centrally symmetric. And what they showed is that the minimal billiard orbit in this case is 4. It's a back and forth orbit, a very natural candidate for the minimal orbit. And this immediately implies the Mahler conjecture in the symmetric case, of course, if Viterbo holds. Turns out Viterbo doesn't hold. So very recently, instead of proving the Viterbo conjecture, they disproved it. The same people, well, almost, Ostrover and Chaim Kislev. But the counterexample they have for this conjecture is not centrally symmetric, and somehow there is still a hope that at least in the centrally symmetric or maybe some other restriction, there is some version of Viterbo should still hold. So anyway, this strategy is not completely dead, it's just further away from us now. Okay, so back to Funk geometry. We need to define some volume that corresponds to the distance. It's a Finstler metric. In Finstler metric, there are at least two more or less canonic ways to define volume. But it turns out that in Funk geometry, or more generally non-symmetric geometries, the symplectic choice, which I will explain in a moment, it makes a lot more sense than any other. So what is the symplectic volume? It's defined in any Finstler manifold in the following way. You consider the bundle of cotangent unit balls over your subset that you want to measure. It lives inside the cotangent bundle where you have the Liouville symplectic form, and you just declare volume to be the symplectic volume of the cotangent bundle. Explicitly, in the Funk metric case, this leads to the following expression. So this is just a measure whose density at the point x is the volume of the polar body taken with respect to x. That's the volume we're going to use, the natural volume. And the projective invariance we were discussing previously translates into the fact that the corresponding volume of Finster submanifolds in Funk geometry is invariant under collineations. Good. So what will we measure? We will measure metric balls, outward balls, because the metric is not symmetric, so we need to be a bit careful. What are outward balls? Those are all points x, such that the Funk distance from Q to x is at most r. Turns out, to our Euclidean eyes, they look like homothetic copies of the body defining the geometry with around the center of the metric ball coefficient, which is a function of the radius. So this function, 1 minus e2 minus r. And we take the volume of those functions. I will be using the notation capital V, P for with little r to denote the volume of the radius r ball. So this stands for volume product for a reason that will become evident in a moment. So we have the VPR at Q, and then we can take the infimum over all balls, over all centers of balls with a given radius. Once again, one can show that this infimum is achieved at a unique point. And we get some family of affine invariant functions for various values of R. So we think about it as functions of the convex body which defines the Funk geometry. So let's discuss the asymptotics of volumes of metric balls. Of course, when R is small, we are in the infinitesimal regime. This is Minkowski geometry. And this is just the volume product of K with respect to Q times the radius to the n. So this is, well, this explains the name, at least. Perhaps more exciting is to look at, at large radius. And here we have this result of Berg, Bernig, and Vernicos, that if the body is sufficiently regular, probably not strictly needed, but anyway, under some mild assumptions, the volume behaves like an exponent with a fixed, n minus 1 over 2. And the dependence on the body is appears here as the coefficient. This coefficient is a known invariant in convex geometry. It's called the centro-affine surface area. It's essentially the integral over the boundary of some curvature function, and also somehow depends on the distance. No, some classical invariant has some meaning. It's evaluation. It's GLN invariant. It's actually characterized by those properties. Anyway, well-studied property, well-studied quantity. And for instance, Blaschke and Ludwig showed that it is uniquely maximized by ellipsoids. So, okay, at this point, one is led to conjecture that this thing should be maximized by ellipsoids for any fixed radius. But before we do that, maybe let's spend a moment talking about Hilbert geometry. That will be instructive. So there was this conjecture that if we define the entropy of the volume entropy in the Hilbert geometry of a convex body, this is a very crude measure of how fast the volume of a ball grows. So you take the logarithm of the volume of a ball of large radius divided by the radius, and the largest thing that can achieve. So going back to what we had here, we are after this number, n minus 1 over 2, but not in Funk, but in Hilbert geometry. So we defined the entropy, and Colbois and Verovic, or at least in the paper, they stated explicitly a conjecture that seems already been known for some time, that the maximal value of the entropy is n minus 1, that it's achieved by hyperbolic metric. Okay, this is now a theorem. It was proved by Tolozan in 17, and shortly thereafter, but published some years later, also Vernicos and Walsh gave completely different proof of the same fact, that yes, that's true. The entropy is bounded by n minus 1. Now, the maximal value is attained by hyperbolic metric, but it's far from unique. If you have a C2 strictly convex body, then it has the very same entropy n minus 1. If we want to have ellipsoids as the answer, we need to ask some finer question. Okay, so going back to the result of this, guys, we have also something similar in the Hilbert metric, that in fact, under some regularity assumptions, the volume is proportional to, well, the exponent with power n minus 1 r with some coefficient that depends on the body in an explicit way, and then they show that this coefficient is uniquely maximized by ellipsoids. Okay, now we're already very confident that the following conjecture must be true, surely, that for any fixed r, if you look at the volume of the ball of radius k, and you choose the worst possible location for a center, so the one that gives you the smallest value, that this quantity should be maximized by ellipsoids, hopefully uniquely. And this actually would imply and sharpen the volume entropy conjecture in Hilbert geometry. And the reason is that Funk and Hilbert geometry are very closely related. So let me briefly explain that. So since the Hilbert geometry is the symmetrization of the Funk geometry, we have this inequality, and that means that Hilbert balls of radius r are contained in Funk balls of twice the radius. We also can compare the volume of the symmetrization of a body to the volume of the body itself. And that means that, the Hilbert volume of a body is bounded by some constant times the Funk volume of the same body, and plugging in this inclusion tells us basically that the Hilbert entropy is at most twice the Funk entropy. And for the Funk entropy, we have this, well, conjectured inequality that allows us to replace k with an ellipsoid and then just conclude that it's what it should be. It's an explicit expression. So unfortunately, we can't prove the conjecture in full generality, but under some assumptions. So here is a setting in which the conjecture is known. K is called unconditional if it is invariant under reflections with respect to all coordinate hyperplanes. So it has some symmetry. And under this assumption, indeed, the Funk-Blaschke-Santaló conjecture holds. And so we get a new proof of the entropy conjecture of a sharper version thereof, but under this extra symmetry. Good. Now to discuss the other bound, the lower bound, which would correspond to Mahler conjecture, let's briefly talk about what happens to the volume under some basic operations. So it turns out that the Funk volume behaves nicely under Cartesian products. If you have two bodies K and L and they form their Cartesian product, then the corresponding the volume of the ball is just the product of the corresponding volumes of balls. So it behaves nicely under Cartesian products, also behaves nicely under duality. So that's something I hope to get to in the end. So for K and for K polar, we get the same volumes. And that means that we can compute easily the volume, the Funk volume, when our body is a Hanner polytope, because recall it consists of products and polars of intervals. And we get something that the most important takeaway from it is that it's the same for all Hanner polytopes. So maybe that's some evidence to formulate the Funk-Mahler conjecture, which we do. And that is what you think, that for any finite radius, this volume is of the ball of radius r is uniquely minimized by either simplices with q at the center of mass, or by centered Hanner polytopes if we work in the class of centrally symmetric convex bodies. And once again, we can only show it for unconditional convex bodies. That's That's our joint result with Constantin, Vernicos, and Cormac, Walsh. So for the volume product, which corresponds to radius going to 0, that's now classical result of Saint-Ramon from 1981. Okay, and now let me talk about what happens in polytopes. So first of all, it's worthwhile to keep in mind that the behavior for large radius in Hilbert and Funk geometries, it depends strongly on the regularity of the boundary. For instance, if you are a polytope, then the geometry turns out to be by Lipschitz to a norm space, and so the volume growth will not be exponential, it will be polynomial. Okay, we will need the notion of a flag of a polytope. So this is a chain. We choose, so FJP stands for the j-dimensional faces of a polytope P, and the chain is a vertex which is contained in, a flag is a chain which is a vertex which is contained in an edge which is contained in a two-dimensional face all the way up to a facet which is contained in the only n-dimensional face, which is the polytope itself. So Vernicos and Walsh, they proved earlier that in Hilbert geometry, the volume of balls in the Hilbert geometry of polytopes is dominated by the flag number. This is the leading coefficient when the radius goes to infinity. The flag number is the number of flags that the polytope has. That's some interesting combinatorial invariant of the polytope. Using the fact that that the volume is projectively invariant, we can essentially repeat that proof and arrive at the same conclusion also in Funk geometry. So again, the flag number determines the large radius behavior of the volume, and it can be thought of as some combinatorial analog of center of fine surface area. Okay, that's good. What are the extremizer of flag number? Well, without any restrictions, it's easy exercise that the flag number is minimized by the simplex. N plus 1 factorial is what you get for the simplex, the number of flags. For the central symmetric case, it's more interesting. So Gil-Kalai conjectured in 89 that for centrally symmetric polytopes, the flag number is bounded from below by 2 to the n factorial, and equality is, equality definitely is attained by all Hanner polytopes. They'll have the same flag number, unique or not. You can conjecture that. There are no counterexamples. And it is known to hold for simplicial polytopes. So polytopes, simplicial polytopes. That was proved even earlier before Kalai in work of Barani and Lovesh. Now, Kalai in the same paper, he actually conjectured a lot of things. This is the most famous conjecture in that paper. That is a special case of a conjecture that was shown to be wrong, which somehow made this conjecture a little bit obscure, but this one remains conjecturally true. And the threat of the conjecture is that, if you count the number of faces of a polytope of all dimensions, then you will be getting 3 to the n. Again, equality is attained by Hanner polytopes, maybe uniquely. Both conjectures are open. This, at least, is known up to dimension 4. So now that we have the Funk-Mahler conjecture, at least for unconditional bodies, we can take the radius to infinity there, and to conclude with a special case of the Kalai's conjecture, as we do, that at least for unconditional polytopes, we do get the conjectured lower bound on the flag number. So, okay, that's good. So, unfortunately, equality cases are lost in the limit. We don't know that Hanner polytopes are the only minimizers, but we will say something about that about equality cases soon. It's also worthwhile to point out that more or less at the same time, two proofs appeared for the 3 to the D conjecture, also for unconditional polytopes, and they also have equality cases. So, well, we're a bit jealous. We also want equality cases, and we have some partial results in this direction. Okay, so for this, let me tell you what is the monodromy group of a polytope. So fix some flag of a polytope, so a face in every dimension. And now fix some number I. I claim that if you fix all the other faces of this flag except in dimension I, then in dimension I, there are just two choices of a face, either the one that you have or another one, which I call Fi prime. So this is easy to see. For example, if you have a flag which is this vertex and then this edge, well, and then say the green face and then the whole cube, then the only other choice is the blue face, which would contain this edge. Okay, so this allows to define the I flip. It's a map from flags, permutation from flags to flags, which switches the ith face from the one you have to the other one that you can have in that flag. Of course, it's a transposition. And the monodromy group is defined as what's generated by all the flips, and they act on the space of flags. And we define the complete flip. The complete flip. What is the complete flip? First, you flip the 0-dimensional face, then you flip the 1-dimensional face, and so on. Yes?
What is it called, monodromy?
I think by analogy. I can't give you a good answer. So here is an example. You have this vertex inside this edge, inside this face. So first we flip the 0-dimensional vertex, then we flip the 1-dimensional edge, and then we flip the 2-dimensional face, and that's the application of the complete flip. Good. So now I can tell you about our two-term asymptotics formula. No reason why it should be. No, definitely in some cases it's not. When I say definitely, I probably should say pretty sure. But I think that if you try it for the cube, it will not be transitive. I didn't try. I tried. I don't remember exactly what was the outcome. I think it's not transitive. I think there are some orbits there. So we are in the polytope. We look at the volume of the ball of radius r around some point in the interior. So there are two terms here. The leading one we already discussed. It's the flag number. The next one already has some geometric information. We like it for that reason. So what's written here? We sum over all the flags the logarithm of the following thing. For each such flag, we apply the complete flip, we get another flag. Then we look at the n-1 dimensional face in that flag, the facets, and we identify it with the vertex of the dual, the polar polytope. So now that's, well, this head stands for the vertex of the corresponding vertex of the polar polytope, and we pair it with the vertex of the original flag. So there is a natural pairing there, and that's what you're looking at. So this expression is clearly natural, governs the volume growth. Also, it allows us to say something about equality cases in the unconditional Colli conjecture. Here is how. Suppose that we have equality in Colli's conjecture, so a polytope with the same number of flags as the Hanner polytope, the conjectured minimizer. Well, that means that we know the equality cases in the finite radius Funk-Mahler conjecture. So that means that for this quantity to be greater or equal than the one for the Hanner polytope, this coefficient must be greater or equal, because this one is already equal. So we have this inequality. But on the other hand, it's clear that the Hanner polytope actually maximizes this thing. It has -1 for every such pairing. It's easy to see. Think of the cube, for example. And that means that also for our polytope, we must have this pairing -1 for every flag. And here is the necessary condition for equality that we obtain. If P has the conjectured minimizer for the flag number, then for any flag that you take, if you apply the complete flip to it, then the facet there will already contain minus the vertex of the original flag. So at first it sounds very strong, like, is there anything else other than Hanner polytopes? But yeah, actually it turns out that there's plenty. There is, for instance, this notion of two-level polytopes, which means that, well, for every facet of your polytope, you can translate it parallelly to cover one time. And then those two facets already contain all the vertices of your polytope. That's a richer family than just Hanner polytopes, and all of them satisfy this. So that's not the whole, well, that's not the whole story. One would expect that maybe we can, what is R? What is R is the complete flip. Yeah, R is the complete flip. Yeah, I was going to say that there is some hope that we can get more terms in this asymptotic formula, and together they will already imply the full equality conditions, but that's technically complicated. We don't yet know how to compute the next coefficients. Okay. So in the remaining time, let me tell you something about duality in convex geometry and how it extends into Func geometry. So here's a couple of classical results. It was a conjecture of Schaeffer that if you start with a convex body, then the shortest closed geodesic. Okay, so you start with a convex body. You look at the boundary inside the norm space for which K is the unit ball. It has an induced Finstler metric. It's an affine invariant construction. So K induces a metric on the boundary of K. And then you can study the geodesics, the closed geodesics of this metric, and look for the shortest one. Schaeffer conjectured that for K and for K polar, the length of the shortest geodesic is going to be the same. He conjectured it because he looked at the two-dimensional case. So the first step was due to Holmes-Thompson, who a few years later showed that those two manifolds, in fact, have the same symplectic volume, which in this area of mathematics nowadays is actually called Holmes-Thompson volume for in honor of their contribution. And Schaeffer's conjecture was positively settled by Alvarez-Paiva more recently, who showed that, in fact, something more general holds. So if you have two convex bodies and you consider K inside the norm space with L the unit norm, and the polar setting, you consider the L polar inside the norm space with minus K polar the unit ball, then those two manifolds have the same closed, well, the same collection of lengths of closed geodesics, as well as the same volume. Another duality is due to Gutkin and Tabashnikov, who observed that there is duality between Minkowski billiards. Somehow those things can be thought of as kind of limiting cases. Well, sorry, the previous one can be thought as a limiting case of this one. So it says the same thing. If you have K inside the norm space with L the unit ball, or L polar inside the norm space with minus K polar the unit ball. So K is your billiard table here, and here L polar is your billiard table, and you look at closed billiard orbits, then there is a bijective correspondence between them, which preserves length. It's actually a very nice picture. But maybe let me skip the details of it. We will see a similar construction in Funk geometry. Okay, so here is how the duality works in Funk billiards. So we'll need two notions from, well, one notion from projective convexity. If you have a convex body in projective space, then polar body consists of all the hyperplanes which do not intersect the interior. Okay, that's the polar body. It's also convex. And we will also make use of the reverse Funk metric, which is what you think it is. Here is how the duality works in Funk metric. So you play billiards here. So you went from Q0 to Q1. You are going in the direction of P0. So every point here has a tangent line, which is a point here. So we're going in this direction. Now we switch. Okay, we can also draw on this picture capital Q1, which is the tangent line at Q1, which is the point where we hit. Now here we're doing reverse Funk billiard. So instead of going in the direction of P0, we will be going in the direction from P1 until we hit the boundary at the point P1, capital P1. This is going to be, or rather the corresponding dual line, which is a point here. That's going to be our new direction in which we go in the original billiard. So every billiard is in fact can be thought of as a dual pair of billiards in the Funk metric in the original one, and in the reverse Funk metric in the other one. And this correspondence preserves things. So here is the general duality result that holds in the Funk metric, and it does not, well, no such results are known, and likely nothing like this holds in the Hilbert metric. So in some sense, the Funk metric is actually more closely related to projective geometry than the Hilbert metric. Okay, so here's the results. We have a pair of convex bodies, K compactly contained inside L, inside RPN. And so the closed billiard orbits inside K in the Funk metric correspond, as we have seen, to the billiard orbits in L polar. Inside the reverse Funk metric of K polar, and this correspondence preserves length. So that's the main non-trivial statement here. And similarly, the closed geodesics on the boundary of K correspond to the closed geodesics on the boundary of L polar in K polar, and this correspondence preserves length. And finally, the volume of the boundary of K inside L is the same also for the dual pair. So those three statements, they extend in the limit. If K is much smaller than L, we recover the previous results that were well, the known results, the Holmes-Thompson duality, the Schaeffer duality proved by Alvarez-Paiva, and the Gutkin-Tabachnikov duality. And also just a nice example. In the case of two periodic orbits. So what is a two periodic orbit? This is when the following holds. You have some, well, this is the billiard table. This one defines the geometry. And the two periodic orbit means that the four tangent lines at those 4 points, they meet at one point. That's a two periodic Funk orbit. And the length of this orbit is just the cross ratio of those 4 points, which is the same as the cross ratio of those 4 lines. That's a classical, super classical fact from projective geometry. So the billiard statement generalizes this to orbits of longer, well, more than 2 points. Okay, so I arrived at the wild speculations slide. So there is another conjecture of Colli, which relates the flag number to the volume product. So for instance, if you one day were to prove the Mahler inequality, then and also this conjecture, then Colli's previous conjecture would follow. And there is some evidence for this conjecture, numerical evidence, as far as I understand. So in fact, we just observed that this conjecture would follow from a reverse Bishop-Gromov type inequality, right? Well, if you have two radii, capital R and small r, then the ratio of the Funk volumes of Funk balls of those radius is minimized by the corresponding ratio for any of the Hanner polytopes. So this conjecture follows from this one when R, big R is small and small r is, big R is big and small r is small. Okay, of course, we have no idea how to prove it. And I would also say that you could also conjecture that the reverse inequality with the ellipsoid, maybe even more natural, the direct Gromov-Bishop conjecture, but that would be wrong. Turns out that it follows from a result of Clartak from some years ago that the conjecture is wrong. So maybe it's just, well, it was very brave of us to call it a conjecture. I would give it no more than 50% chance of being true. Okay. Another wild conjecture is that, it seems that things, the relationship between minimal billiard orbits and volumes should extend, at least to some extent, to the Funk setting. This two periodic orbit, which plays a key role in the flat case, exists just in some cases and in general conjecturally also in the Funk geometry. So some inequality like this would shed a lot of light on the Turbo conjecture, on the Mahler inequality. So I didn't say the alpha k omega would be the least billiard orbit in the billiard table omega with respect to the Funk geometry of k, and here we have just the Funk volume of omega. So conjecturally, the volume should bound from above the least orbit. Okay, so with this, I will finish. Thank you very much for your attention.
Question about the conjecture of Colli at the end of your talk. Just wondering, so for this conjecture and for each of the polytope ones, I was interested to know, and I think you said it for some of them, but for this one, what other polytopes is there a class of polytopes that is expected to be the specific class to have equality in that bound?
Hanner polytopes.
Pardon me?
Hanner polytopes. Yeah, so for Hanner you would get equality, and yes. Let's see if I'm right. Here we get 2 to the, so the volume product of Hanner is 4 to the n divided by n factorial. So you would get 2 to the n and factorial. Yes, Hanner polytope would be conjectured equality cases.
And are there any other classes of polytopes that maybe generalize those to where you say go a little above the bound that you maybe want to like close to this minimal amount?
So I have seen some work with flag numbers close to Hanner polytopes for which these inequalities were proved, I think. But for this conjecture, I don't think so.
So you were talking about the most problems for the minimum and the maximum of the volume product.
Yes.
Can you make sense of critical values?
Yes. So I mean, for instance, it's known that Hanner polytopes are local minimizers. But just critical points, I don't think that was considered.
Let's thank our speaker again.